Hey there, it's Mr. Moeddin with today's area lesson. This time our topic is area of regular polygons. Let's go ahead and dive in. Recall that a regular polygon is a figure, a shape, with equal side lengths and equal angle measures. So in every one of these shapes, all the side lengths are the same and all the angle measurements are also the same. So for example, in this pentagon, you'll notice that it should be marked that all of these are congruent and all of the angles are also given to you as congruent. Same for this regular hexagon right here. By contrast, while this shape here, drawn by a first grader's drawing of a house, is a pentagon, it is not a regular pentagon because not all the sides nor angles are the same length. So we've seen that kind of definition before, but the key idea that we need to build up to is area of this kind of shape. And if you recall, most of our year has been spent dealing with triangles in one form or other. We spent several months on triangles, really. So we're going to use that leverage to help us with this particular kind of shape as well. So if we split up any one of these shapes by first identifying the center, and then connect from the center to each one of the vertices, we end up with the same number of triangles as there are sides. So for example, in this hexagon, finding the center and then going to each one of the vertices, I have 6 triangles. Moreover, each one of these triangles is congruent. I didn't draw them very well, but each one of these triangles should be exactly the same size as any other. Look at one more here in the octagon. One could imagine the center here and then radiating out to each vertex. Drawn pretty badly, but I think you can see that each one of those triangles should be exactly the same as any other if they were drawn better. So there's a key term here we need to know, and that term is called the central angle. As you might imagine, the central angle is an angle located in the center. That's kind of a no-brainer. So all these orange angles here that I'm marking are going to be central angles. And because all of these red triangles in each individual shape are congruent, all of those orange angles are also congruent, not in every shape to every other, but within every shape. So for example, each orange angle with a single stripe here is going to be the exact same size. And each orange angle with a double stripe here is going to be the exact same size. And likewise down here with triple stripes. So the central angle measurement can be found, like exactly how many degrees it is. We've established what it is. We've established that it's the same as many of its neighbors, but how big is each one? How many degrees, for example, am I looking at in this angle right here? Well, you'll notice that all of these angles here in tandem create a full circle. So I'm subdividing that black circle into 5 individual parts in this case. In this case here, I'm subdividing this black circle into 6 equivalent parts. And over here, I'm subdividing the circle into 8 equivalent parts. So the measurement of each one of these angles, these central angles, should be equal to the total of 360 divided by the number of sides. So the measurement of this angle in the octagon is exactly 45 degrees. By contrast, the measurement of this angle here in the pentagon is exactly 72 degrees. If each one is 72, then you get 360 in total. What do you think this one here should be? Well, same idea, 360 divided by the number of sides, and we get 60 degrees. So you can see that as the number of sides increases, the angle measurement decreases. It gets narrower and narrower and narrower and narrower. So in this decagon, for example, you can imagine a lot of tall, skinny triangles here. So each one of these angle measurements is smaller than it was back here. So this brings us to the following formula. It's very important. The measure of a central angle in a polygon with n sides, which in general, remember, we call it the n-gon. The measure of the central angle is exactly equal to 360 degrees divided by that number of sides. So 360 by 8, 360 by 5, whatever it might be, 360 by the number of sides. Now, before we actually get to area, we have to define another important term. We just saw central angle. We're going to also have to identify this term called the apothem. So this is a fairly unusual word. The apothem, you can see through a couple visual examples here, refers to a segment length in a regular polygon. So each one of these here is an example of an apothem. So that length is defined thusly. It's a perpendicular distance from the center directly to the side in a regular polygon. So none of these red lines back here are apothems. You'll notice they go from the center to a vertex. An apothem goes from the center to the side. Another way to think about it is it's the height of all these little triangle slices. So if you think of this as like a quesadilla crunch wrap from Taco Bell, each one of those little triangles there, then this would be the height of one of those triangles, as you can see here. So the apothem is that height length. Okay, building up to an important formula. The formula for regular polygon area looks like this. This particular polygon has, I believe, 8 sides, but the number of sides here is kind of irrelevant. We're just going to call the number of sides n in general. So we have n sides. Each one has length s. So I have s, and so on. What that also means is that I have n triangles. The number of triangles is equal to the number of sides. When I say triangle, I'm referring to these larger shaped ones. So if I take one of these representative triangles, let's make this green. If I take this green triangle here, I know that its area, if I sort of rotate it, the side length here is called S still, and this is still the apothem. So what's the area of this particular triangle? Well, in general, it's base times height times 1/2, but the base is S and the height is A. So for this particular triangle, the area of this triangle is 1/2 S times A. So that's the area of one individual green slice here. But I have n green slices, right? I have many of them. So I'm going to multiply this individual area by n, because that will give me the total area. I have n of these little green triangles, so multiply it by n to get n times, and I have the total area. So let me do that work over here. That's 1/2 S times A, that's the one individual triangle, multiplied by n, which is the number of triangles. So one triangle times the number of. Now you'll notice here something kind of clever happening. We're multiplying S times n, or S n times. The reason I went through all that work here to mark out all the S's is this length is called the perimeter. I've literally gone n times around this shape, S distance. So that length in orange is the perimeter of our figure. So S times n will give us the perimeter. So our final formula here is 1/2 perimeter times A, which recall is the apothem. So here's the important formula. 1/2 perimeter times apothem. Let's take a look at a couple examples. Find the area of this figure to the nearest tenth. Be sure to include units. So I have a couple of steps here to kind of guide your thinking. We either need the apothem, or we're given it. Sometimes we're given it, sometimes we're not. Notice that in this case, we're given the side length. The side length is 10, so we need to be able to find the apothem. So how do we do that? Well, first we need to find the central angle. Well, this is a 5-sided shape, so the central angle should be 360 degrees divided by 5, which earlier I believe we saw was 72 degrees. So going to my figure here, if I divide this into 5 congruent triangles, then 72 degrees is any one of these angles here. So that means this guy right here is also 72 degrees. But the apothem here in red is bisecting that 72. So if the orange angle is 72, then how many degrees is this green angle? That's right, it's 36 degrees, half of 72. So there we've bisected our angle. So let me take a look at this blue triangle here up close. So we have a right angle. The red length here is the apothem that we would like to find. We know that this angle right here, we've just established, has been bisected from 72 to give us 36 degrees. And what was 10 as the side length of my original pentagon, that means that this part right here should just be 5 inches. That side length has also been bisected by the apothem. So I want to find the side length A. I have that my side length here is 5. As you can see here, trigonometry is probably our best option because we have an angle and a side and a missing side. So let's find the appropriate trig function. Well, from my reference angle of 36 degrees, 5 is directly opposite. And my apothem here is aptly labeled as the adjacent. So opposite and adjacent should lead us to our very useful trig ratio, the tangent ratio, SOHCAHTOA, TOA, opposite over adjacent. So tan of 36 is equal to opposite, 5 inches, over adjacent. So busting out the calculator here, tan of 36 is 0.727. I'm going to cross multiply. So this will give us 5 equals 0.727a. Divide both sides by that decimal value. And we get 6.88 as our apothem. So this length right here is 6.88. Okay, so we now have that. Step 2. So that was kind of a long step 1, but that's most of our work already, actually. Step 2, find the perimeter. Okay, well, the perimeter should be fairly easy. The length here in lime green is 10. How many of them are there in the outside of this shape, the edge of this shape? Well, there's 5. So the perimeter would be 50 inches. Pretty straightforward. And finally, let's use our formula. Our formula says the area is 1/2 perimeter times apothem. The perimeter we've just established to be 50. The apothem we calculated to be 6.88. So 1/2 times 50 times 6.88 will give us an area of 172 square inches. I'll label my work here to make it a little clearer. There was step A, here was step B, here was step C. Step 2 is sort of straightforward with the 50 there, and then step 3 is right by 3. So we're given a side length, we have to find the apothem. So this problem here is a little bit different in that we're given the apothem from the get-go. Same question, find the area. So let's take a look at what we can do here. Step 1, find the apothem or the side length. Well, the apothem's given, so it's got to be the side length then. Okay. Let's see what we can do. Find the central angle. Well, this is an octagon. There are 8 sides. So the central angle here would be 360 divided by 8, which earlier we got to be 45 degrees. So drawing out my triangles here. Would be something like this. And each one of these orange angles is 45 degrees. What the apothem here does, though, is to cut that into halves. So what that means is that this green angle here is half of 45. In the big picture, looking at step 2, we're going to need the perimeter, which means get the whole side length. But sort of as an intermediate step, remember the apothem here creates a right angle. In this little blue triangle, I take this guy out here. We have a 22.5 degree angle here. We have a 15 centimeter side right here. Well, I have a choice. I could find this length here in purple. I could do that. But since I ultimately want to find the perimeter, it'll be much more beneficial for us to find this length here in magenta. So let's find that guy. Let's call that guy the opposite. I'll just call it X for now for a missing piece. But that side length is going to be opposite. 15 is still adjacent. So just like before, tangents are our go-to. So tan of 22.5 degrees is equal to opposites over adjacents. Opposite over adjacent. So tan of 22.5 is 0.414. Multiply both sides by 15. And we get a side length of 6.21.
This side length, can you clarify? This length right here, we just found to be 6.21. Well, that is the side length of the triangle, it is not the side length of the entire original octagon. 6.21 refers to this piece right here. So if that's 6.21, then how long is this brown piece right here, for example? What would that be? That's right, it would be double. So 6.21 times 2 will give us 12.42. So the actual side length here is 12.42. So to find the perimeter, so if each side is 12.42 centimeters, there are 8 sides in total because it's an octagon. So multiply that number by 8 in our perimeter. The total length around 12.42 is actually 8 times will give us 99.36. So we multiply that by n, which in this case is 8. Okay. Almost done. Area equals 1
perimeter times apothem. Well, the apothem's been sitting here unused. That was 15. So 1/2 times 99.36 times 15 will give us an area of 745.2 square centimeters. So compare and contrast these two problems. They're very similar in a lot of ways, but there are some subtle differences. One, in this problem, we were initially given, it's kind of hard to tell with all this color, we were originally given this red length right here of 15. We were given the apothem. We had to find a side length, which was 12.42. By contrast, earlier we were given the side length, 10. We had to find the apothem, 6.88. So pretty similar, but some subtle differences, namely right here in the trig step. Our last example here is pretty tricky. It asks us to find the shaded area. So we've seen problems like this before last week. This is a composite figure. So a good plan here might be to find the area of the circle and then subtract away the area of the pentagon. So the method here is going to be circle, which is bigger, minus pentagon. So first step to find the area of the circle, the formula for that, if you recall, is pi radius squared. So the radius here is 10 for the circle. So the formula, plugging that in, would give us pi times 10 squared, which is 100 pi, or 314.2 square centimeters. So that's the area of the whole circle if the pentagon were not cut out of it. We, however, also need to find the area of the pentagon, which is this new step that we just learned about the area of a regular polygon. This time n is 5. So that's going to be 1/2 perimeter times apothem. And notice that in this problem, we're not given either a side length nor an apothem. This 10 here is a radius. So a side length would be this red piece, which we don't have, and the apothem would be this blue piece, which we also do not have. So we need to find both of those, and that makes this problem particularly tricky, but we can persevere and find it out. So first, if I draw all of the 5 triangles here, just like before, 360 divided by the number of sides, 5 in this case gave us 72, which means that this green length here, this green angle here would be half of that, or 36 degrees. So looking at this triangle in some more detail would give us the following. We have a red length, which is part of the pentagon side. We have a blue length called the apothem. And then we have this purple length here, which is given to us as 10. Now you've just established that this angle measurement here is 36 degrees. So we need the apothem and the side length in this case. We need both. Let's find the apothem first. So A is adjacent to my green angle of 36. The best way to describe that 10 would be hypotenuse. So adjacent hypotenuse should lead us to the cosine ratio. So cosine of 36 degrees is equal to adjacent over hypotenuse. So cosine of 36 is 0.809. Multiply both sides by 10, and we get 8.09. So that guy right there is our apothem. We now know that this length here in blue is 0.809. Sorry, 8.09. Okay, we have our apothem. We still need to find this little red guy right here. And there's a couple of ways we could go. We could use trig again, nothing wrong with using some more trig. However, it might be faster to use a little bit of Pythagorean theorem, because now that we know that this length right here is 8.09, we now have two sides of a right triangle. So all I got to do to find this opposite length, we'll just call it x here, would be x squared plus 8.09 squared equals 10 squared. So if I solve that out real quick, looks like we get 5.88. So this red length here is 5.88. So going back to the original figure, that means that in the triangle, this is 5.88 right here. Which means that this full brown length is double that. So 5.88 times 2 gives us 11.76. So we've already done a bunch of work here already. Let's take stock of what our goal is. Our intermediate goal is to find the area of the pentagon. We needed the perimeter and the apothem. We found the apothem earlier to be 8.09, so that's going to be going in right here. One half perimeter times apothem. Well, we just got the side length to be 11.76 after a fair amount of work. So 11.76 is one side. This is a pentagon, so I have 5 of them. So 11.76 times 5 gives us a total perimeter of 58.8. So 1/2 perimeter times apothem will give us the area of the pentagon. So 1/2 times 58.8 times 8.09 gives us an area of 237.85. So that's the area of the pentagon. The area of the circles have been sitting here earlier to be 314.2. So all we need to do is to subtract them like our original plan said, circle minus pentagon. So 314.2, actually it should be 15, minus 237.85 gives us a total rounded area, when I subtract those two, as our original plan was, of 76.3 square centimeters. And that wraps it up. Hope you're doing well. See you soon.